And then with that, let me introduce our speaker. I'm very happy that we have Jennifer Chayes here today to give a talk. She is a professor in 4 different departments and schools at UC Berkeley. These are electrical engineering and computer science, that's one school, mathematics, statistics, and the School of Information. She is also the associate provost in the Division of Computing, Data Science, and Society, and also the dean in the School of Information, which I believe is a new school, if I'm correct. She's had numerous awards. I want to highlight just a few of them here. For one thing, she founded 3 interdisciplinary labs at Microsoft. She is a member of both the National Academy of Sciences and the American Academy of Arts and Sciences. She's earned an honorary doctorate from University of Leiden. She's also received the Women of Vision Leadership Award from the Anita Borg Institute. And then in terms of some SIAM recognition, she is a winner of the John von Neumann Lecture Award. And with that, she'll give a talk on Graphons and machine learning, modeling and estimation of sparse networks at scale.
Hi, thanks so much, Mason. I'm going to correct one thing, which is that the School of Information has been around for a while, but the new entity is the Division of Computing, Data Science, and Society, which comprises the School of Information, the Department of Statistics, the Department of Electrical Engineering and Computer Sciences, and data science connections with all of the other colleges and schools on campus. So it was data science that was the impetus for starting this new entity. And it's the biggest reorganization of Berkeley in over 30 years, and it's all around data science. So, it's very appropriate that I'm speaking in this conference, and thank you so much for having me here. So what I'm going to talk about is Graphons and machine learning, modeling and estimation of sparse networks at scale. And oh my, this is not advancing, so I'm just going to advance it. Nothing is advancing. Hello? I hope I'm here. Good. Okay. So the outline. I'm first going to talk about the motivation for studying Graphons, why we came up with the notion of Graphons, which now is 15 years ago. I'll talk about graph convergence and the limits of these graphs. I'll talk about generating random models of graphs, a huge generalization of things like just the random graph model. I'll talk about estimating and predicting networks. So this is the way of learning networks. And then I will also talk about one application, which is an algorithm on sparse networks at scale. So our motivation was threefold. The first motivation was we wanted to come up with the correct notion of a limit of graphs. It surprised us. All of this work is joint with Christian Borg's, and much of it is joint with other people, and I'll tell you who they were as I get to those parts of the work. But what we wanted to do was preserve essential properties of finite graphs in the sequence, get a notion of a limit which was neither too weak to, if it were too weak, it would have allowed any, all different kinds of graphs to converge to the same limit. And if it was too strong, we would just get completely different limits of things that we thought were similar. Then the next question is, how do we non-parametrically model real-world networks at scale, and how do we learn that non-parametric representation from data? And finally, given a very sparse sample of a denser underlying network, how do I predict unobserved properties, latent features of these networks? Okay, so the first of the 3 questions has to do with similarities of networks. So if you look at this picture of a brain cell and this picture of the universe, they look remarkably similar in many ways. And you look at this, and I, coming from statistical physics, mathematical statistical physics, asked by analogy to thermodynamics as a limit of statistical physics, or by analogy to differential equations as the limit of an interacting particle system, is there a meaningful way to compare large networks and define limiting networks? And we'll spend the first part of the talk talking about this. The second question is modeling and machine learning of networks. So if I look at a snapshot of Facebook or LinkedIn, how do I take a single snapshot of the network and from that learn to predict properties of the network when it's twice as big? How do I predict the network parameters, or better yet, a non-parametric representation of that network? And you know, if I want to do things like A/B testing or collaborative filtering on the network, how do I do that with a single snapshot of a network? And the answer is that I want to estimate the graph limit, which turns out then to be a non-parametric network model corresponding to that snapshot, and use that estimate to predict how the network will look at a later time or a larger size. And this gives a consistent estimation for really large networks like Facebook and LinkedIn. And I'll talk a little more about that. Okay, then the final question is, how do I infer a missing entry in a sparse network? Like if I look at the Netflix network of users and movies, it's not like there are lots of people who are identical to me from whom I can predict what I'm going to like. The network is pretty sparse. I have not rated the vast majority of the movies on Netflix. And the vast majority of the movies do not have a very large number of people having rated them. There are other questions like this when Amazon wants to recommend to you products to buy, or if a development economist goes to India, let's say, and tries to sparsely sample a network, and from that predict who might be connected to whom. Okay, so here's a preview. We're going to take a graph, which is a set of vertices and a set of edges represented by an adjacency matrix, telling us either that node X and node Y are not connected to each other, it's a 0, or connected to each other, that's a 1. And from that, we're going to take a limit, and the vertex set is going to become a sigma finite measure space. It is going to have a set of nodes and a sigma algebra and a measure on the distribution of properties of those nodes. So it might be a measure telling me, oh, you know, I'm so likely to have someone who has this set of attributes in my vertex set. And it's a symmetric measurable function which replaces the adjacency matrix, which will tell me the density in some way of one site connected to another site in the limit. So here's a heuristic picture of what we're doing. What I want to do is I want to take a graph and I want to represent it as an adjacency matrix, as this n by n matrix. And if I have an edge, I'm going to color it black. And if I don't have an edge, I'm going to color it white. And then in a very hand-wavy way, I can take something like this half graph, and I can take the limit of it and get this picture on the unit square. Just imagine that in my adjacency matrix, each of those edges are of length 1 over, each of those blocks are 1 over n by 1 over n, and I get something on the unit square. I could similarly take the random graph, GNP, at density 1/2. I get all these black and white nodes. and they converge to the constant function w equal to 1/2. However, there's a problem here. What about permutations of the vertices? I could take that, first I could take this graph, which looks like it does in this picture, and I could just relabel the vertices. I could do a permutation of the vertices, and then it looks like this other picture. And so which limit do I take in a heuristic sense? And in a non-heuristic sense, with Lovas, Christian Borges and I, a long time ago for dense graphs, showed that the limit is unique up to measure preserving bijections on the unit square. So when I get a limit, it's not just one picture, it's all the pictures that are consistent with that up to measure preserving bijections. Okay, here are a few more examples. I could have a randomly grown, dense, uniform attachment graph, and I'm going to represent it ordering by degrees. Okay, so I have the very highly connected ones in the upper corner there, and then if I look in a heuristic sense, it looks like it converges to this function 1 minus max of x and y, and of course all measure preserving bijections of that function would also be consistent with this. Or I could take a randomly grown dense preferential attachment graph ordered by degrees once more, and here it's a much wider range of degrees. And what happens is the function is now an unbounded function. It's c log of x log of y, and I'll measure preserving bijections of that. But you see, it's a qualitatively different function in the sense that it's unbounded, and that is reflecting the large distribution of degrees. Okay, so let's first look at dense graphs, which are much easier. Dense graphs are graphs in which the number of edges scales like the number of vertices squared. And let us come up with a very useful notion of convergence. And as anyone who's done analysis knows, metric convergence is a really useful notion if you can get it. So the question is, how do I compare two dense graphs of different sizes, possibly even on different spaces? So what I want to do is I want to use something called the Fries-Kahn-Cut norm of the adjacency matrix, or of the graph, to later define a distance in between two graphs. So what the Fries-Kahn norm says is that I should look at the max cut of my graph. So I should divide the graph up into two pieces such that the edges that I cut between those two pieces are a maximum. If I have just edges or no edges, I'm cutting the maximum number of edges. If I have a weighted graph, I'm cutting the maximum weight of the edges. And then I want to take two graphs and I want to subtract their adjacency matrices from each other, and then take the cut norm of that difference. And finally, of course, what I want to do is I want to minimize overall permutations of the vertices, because a good metric can't depend on how I order the vertices. And I will call that object taking the max cut between the adjacency matrices of the two graphs, doing the min over all permutations. I will call that the cut metric. And a good notion of metric convergence of a sequence of graphs. Oh, and of course, if these graphs are in a different number of vertices, I have to in some way scale them to be of the same size, things like that, which I can do just by blowing up vertices to the kind of least common multiple of the two graphs. And then my notion of metric convergence is that I have a sequence of finite graphs. They converge to a function w on the unit square if that difference converges. Okay, and in more complicated situations, like if the two graphs are on different spaces, then I'm going to have to also do all couplings between those two spaces and minimize over those couplings. So there are various notions that there were 5 of us who did a long series of papers, starting about 15 years ago and running through about 10 years ago. It was Christian Borgs and I, Latsi Lovas, Vera Shoge, and Kati Vestergambi. And what we did was we looked at a local convergence notion. We said, let us think about looking at the homomorphism of a small graph into a large graph. So G is like the network I want to look at, and F is like a small subgraph of that. So maybe an edge, maybe a triangle, maybe a square, maybe a Peterson graph. And the subgraph density is the probability that a random map from, let's say, the triangle to the big graph is a homomorphism. And that is actually the triangle density of G. So I could look at the triangle density, the edge density, the square density, the Peterson graph density, all finite graph densities. If all of those converge, then I say that the sequence is subgraph convergent. In some of the literature, you'll see this called convergence from the left. And for dense graphs, one of the first things that we proved was that all subgraph densities converge if and only if there is metric convergence. We had many other notions of convergence, global, in this case, notions of convergence for dense graphs. Instead of looking at homomorphisms of a small graph into a large graph, which is the right way to measure subgraph densities, we could also look at the homomorphism density of a large graph into a small graph. So what would this be? This would be really like a statistical physics model. The small graph would represent the interactions in the Hamiltonian of my model. So the Ising model would have interactions, nearest neighbor Ising model would have interactions with nearest neighbors, okay? And it turns out that we can look at homomorphisms of big graphs into little graphs representing statistical physics models, and we could look at convergence of all microcanonical free energies. Computer science, we might want to look, going along this sequence, at max cuts and min bisections and multi-way cuts and bisections. And we might ask for convergence of all max cuts, min bisections, and multi-way intersections of those. We might look at Semiretti partitions and we might mod out by them and come up with a notion of quotients and ask for convergence of those. A more kind of probability type way of looking at this would be, let us hold both the vertex and the edge densities fixed and come up with a large deviation rate function which corresponds to entropy of these graphs, of each of the graphs along the sequence with the vertex and edge densities fixed at different numbers, and ask that all those entropies converge. Well, it turns out that for dense graphs, metric convergence, subgraph convergence, and all 4 of these global notions of convergence are the same. The first 3 were done with that large collaboration, and the large deviations rate was done with David Gamarnik, and all this work is with Christian Borgs. Okay, the next thing that we looked at, first with Jeff Kahn and Latsi Lovas, and later with David Gamarnik, was sparse graphs of bounded degree. Okay, these are really different. They're much more fragile. There is no good notion of metric convergence here. There were older notions of convergence. In particular, a very useful one is called Benjamini-Schramm convergence. And in this, what you do is you choose a random vertex in your graph, and you look at convergence of graph rooted at that random vertex. So you keep doing this along the sequence. And it turns out that you get this Benjamini-Schramm convergence if and only if all subgraph densities converge. But for sparse graphs of bounded degree, this is a strictly weaker notion. So convergence of free energies is a strictly stronger notion in what you would call the low temperature, the ordered phase of the corresponding statistical mechanical model. And the large deviations convergence is just a strictly stronger notion. So we can define these notions of convergence, but in sparse graphs of bounded degree, they are not equivalent. Now, what we really care about are sparse graphs of unbounded degree. For example, power law graphs, things that, for example, led to that W equals, constant times log X, log Y in one of those first pictures. Okay, and why do we care about that? Because a lot of the networks that we want to model and estimate in the real world, networks that reflect many human interactions, are sparse graphs of unbounded degree. And here, local notions like subgraph frequency are just too fragile to give a nice notion for sparse graphs. It turns out there is a different kind of notion, which I'm not going to get much time to talk about, which is more of a statistical approach to it that will give some other good local notions. But let us just look at a really easy sparse graph to think about. Let us look at the random graph GNP. So every one of our n nodes is connected to every other node with probability p. So p, let's look at n to the minus 2/3. So how many edges do I have? Well, I have n times n for my 2 vertices, and I have n to the minus 2/3 for my 1 edge. So that's n to the 4/3 edges. How many triangles do I have? I have n times n times n for my 3 vertices, and n to the minus 2/3, n to the minus 2/3, n to the minus 2/3 for my 3 edges. That means I have n triangles. So I could very easily remove all n triangles while not changing the edge density at all. Well, then clearly I cannot have convergence of subgraph densities, okay? So most real-life networks are sparse, but with existing dense graph definitions, any sequence of sparse graphs converges to the trivial limit. So the limit of the W's is the 0 function. Many real-life networks have power law, degree distributions, and other distributions in which the maximum degree over the average degree diverges, even though that is bounded for dense graphs. So the goal is to develop a theory which works for sparse graphs with mild assumptions on the density. And the first way in which we did this required reformulating Semeretti's lemma, which some of you may know about, for sparse graphs with unbounded degree. There had been a lot of work on Semeretti lemmas for sparse graphs, but they were with bounded degree. Okay, so the first notion we came up with was following Boabash and Reardon, who had done some work, some wonderful work in 2010 for doing this on graphs of bounded degree, or at least where the W function turned out to be bounded. And in a series of papers, Christian Borgs and I, with, let's see, who was it here? It was Henry Cohn, and I will come up with the last name. I don't think Z is the right initial, actually. Came up with a notion of sparse, oh yes, it is. It's Yufei Zhao, whom a lot of you know. Okay, so what we said was, we have this function W super G, or W super Gn is that representation. I'm going to represent the height of W by a little height on that graph. And this is when I have my, n vertex graph, which I'm representing on the unit square. And the problem is that this is going to converge to 0 if I use the old notion. So what I'm going to do is I'm going to divide through by this norm, and I'm going to call that the rescaled W. So I'm dividing through by something that goes to 0 in the hopes that what I get will not go to 0. And I call a graphon convergent if these rescaled graphons along the way converge to some function. Okay, this has a chance of being a non-trivial function. And what it does is it leads to generalizations of many of the results that we got for dense graphs. In particular, the notions of convergence for dense sequences, provided that the average degree of the graphs along the sequence diverges. Okay, there's a totally different notion that we worked on with Nina Holden a number of years ago. So this is Christian Borgs, Henry Cohn, and I with Nina Holden. So instead of dividing through by the norm, which is going to 0, we said, let us scale the space by the square root of the norm. So then we take the unit square and we turn it into the positive quadrant. So we stretch everything out. And we say that something is convergent in this stretched sense if those approach a function in the positive quadrant. So do these notions of convergence give subsequential convergence for arbitrary sequences, which is what you would want? And the answer is no. Mass can disappear in the first case up to infinity, up, and in the second case out to infinity. And the solution is that we developed a theory for sequences that obeyed different notions of regularity, which ruled out these pathologies. And then we got generalizations of many of the results for dense graph sequences, including global notions of convergence, as long as the average degree diverges. The advantages of the first definition are that we can get power law graphs, we can get GNPN, the degree distribution converges, the generating model can be estimated from a single sample. I'll be talking more about that. And for bounded graphons, the estimation can be done differentially privately. And I will also talk about that. The second case, there are very long tails. The vertices, this is a projective model. It turns out the vertices which appear earlier have larger degrees. A lot of statisticians like this more because it corresponds to a projective sequence, and it leads to a projective exchangeable family and a generalization of the Aldous-Hoover theorem. So these both sound great. Can we get a sequence which converges in both senses? And the answer is only if it's dense, which is therefore the trivial case here. But if either of these converge, then the average degree diverges. Okay, so for both dense graphs and sparse graphs of unbounded degree, we've seen how to get from a sequence of graphs to a limiting graphon. If I hand you a limiting graphon, if you walk in your first day of work at Facebook and I say to you, here's the graphon of Facebook, how would I have gotten that? How would I have gotten that non-parametric approximation for you? And what graphs can I generate from that? So generating first dense random graphs as networks, the best known model for this is called the stochastic block model. Here you have k species of particles. You can think of k colors, red, blue, green. I have a matrix of probabilities that color A is connected to color B, so red to red, red to blue, red to green, a symmetric matrix. Since these are undirected graphs that we're going to generate from it. But let's think of a newer non-parametric model. Let's think of having a feature space and a probability distribution over that space and a function telling you the likelihood that different points in that space are going to be connected to each other. So here what I'm going to do is I'm going to choose endpoints x1 up through xn according to some distribution pi. Let's think of pi as having some attributes of human beings, okay? So it could be my height, it could be my age, it could be my maximum educational level, it could be whether or not I like biology, whether or not I like mathematics, whether or not I like all these other things. So that is my space, omega. I have a probability distribution over that, and I generate these points, okay? And then W of X and Y is going to tell me the likelihood that individuals with those features are going to connect to each other. And I'm going to denote the resulting random graph. It's an inhomogeneous random graph, and I'll represent that as W. Okay, so how do we do it if it's sparse? Bolobosh and Reardon did this for sparse cases in which you got a bounded W out in the end. And again, they had a space omega, a probability distribution over that space, and a target density, okay? And this target density is kind of like dividing through by the norm of W before. And so they got this inhomogeneous random graph with this target density. With Yufei Zhao, we generalized this to unbounded W's. And we showed that what you can get is, for example, power law graphs, that these will converge if the density goes to 0 and the average degree diverges. The result is exchangeable, but it's not projective, okay? To get from one to the other, I might have to, from one graph in the sequence to the next, I might have to reinsert edges. The Graphon process is projected. It goes back to a Caron and Fox paper. Roy and Veitch, or Veitch and Roy, I think, and Christian Borks, Henry Cohn, Nina Holdit, and I studied this in 2016. And here we have a sigma finite measure space and a Graphon. And what we're going to do here is these points are going to be a Poisson process of points. And we are going to connect them with a probability, W of X and Y. So we can again think of omega as representing attributes. Then I'm going to remove isolated vertices, so different kind of process, and things that haven't connected when I flip my W-weighted coins. And so by removing the isolated vertices, I still have a birth time for every vertex, but I consider it hidden until it appears. So let's look at an example of that. Here I generate these 4 individuals with various sets of attributes. I go and I flip my W-weighted coin, 4 choose 2 times. And between 2 and 3 and 2 and 4, I get a 1. All the other times I get a 0. This is my graph at time T1 after those 4 points have been generated. And point 1 does not appear because it didn't get connected to anyone. By time T2, 3 more points have appeared, and a lot of other coins have been flipped. And lo and behold, point 1 now appears because it got connected to point 7. Point 6 got connected to a couple of the existing points. Point 5 didn't get connected to anyone by time 2. Okay, I'm not going to be able to talk to you much about that second one, which is really cool. That's a whole other talk. This is just the difference in appearance of the 2 of them. The second one has a lot more dust going out. Okay, finally, what I want to do is I want to do estimation, okay, on these networks. So I want to say, given a graph, I want to tell you that I can statistically consistently estimate it. By the time we had produced some of this other work, people were already using it to estimate, but there were no theorems that you could do it statistically consistently. So in the general case. So, you know, what people used to do estimation was that they would assume that the model was a stochastic block model. They would estimate the parameters of the model using maximum likelihood and generate a new graph using the estimated parameters. This was not stable to model misspecification. If I assume it's a stochastic block model and it is not, I'll get something out, but it won't be stable in any way. A non-parametric approach is to model G as a W random graph. So I'm going to model Facebook as a W random graph. I'm going to estimate an approximation to that function. And then once I have that function, I am going to generate new random graphs with that function in the same way that I generate new random graphs, you know, for example, for GNP using probability P. But here I have to go through this other process of generating the X1s up through XNs and connecting them. So our task is to estimate an approximation from a single sample. This work is finally about to get published after 5 years. It got lost in the annals of statistics refereeing process, but it's about to get published now. And we show that if W is in L2, if rho goes to 0 and the average density converges, diverges, then we can estimate this. Maximum density diverges. Okay, now can we do this privately? And there actually is another paper in here later, which I will mention on the next slide. But you know, we all know the privacy problem for databases. Given a database, you know, what information can we release to protect the information of the individuals there? How much can I query that database? This is even worse for graphs because often your connections on the graph reveal information on you. Over 10 years ago, it was shown that you could very accurately guess people's sexual orientation by their connections on Facebook, even if they didn't state their sexual orientation, just from their connections. So we are going to turn to differential privacy, okay, which is a notion of Dwork and Smith and others. The definition is that a random, so for the case of networks, okay, node privacy, we say that a randomized algorithm A is node private if I have two graphs that differ by one node, let's say me. And all events, the probability of all events I can look at in the output space should be basically 1 plus or minus epsilon different in their ratio. So there's not much difference if you query with me in the network or without me in the network. There's a notion of edge privacy, which is much easier to achieve, but it's not as useful. Our task was to do a node private estimation of general sparse graphons. We showed that if W was bounded, you could do this provided that rho n was going like log n over n. Furthermore, a couple of years later, so this was with Adam Smith, a couple of years later with Zadik, we showed that this can be done with no loss of accuracy as epsilon goes to 0. So this was obtaining matching upper bounds, which was actually very surprising. Okay, so here's where we stand. And we have about 5 minutes now to do an application of this. So let's look at an algorithm for network completion on a sparse network. So we could do this, for example, on Netflix, or we could do it to socially complete a network that was being sampled by an economist, or we could do it to do network completion to say what's the odds that you're going to be sending email with some other person, or you know, they're going to like your post. That would be a directed version. So what this really is a matrix completion problem. Okay, I am row U, that's me, and column I is a movie, and I want to know what are the odds that I'm going to like it. Well, the Aldous-Hoover theorem, just the simple form of it, tells us that our matrix can be written as a function on these two latent variable spaces with some noise. And so here we are, I'm doing that because Aldous-Hoover told me that I could. Now I'm going to take the expectation over this, observing each entry sparsely, independently with probability p, with a really sparse p, because that's what I tend to get on these sparse networks, right? I either only sparsely sample them or the entries are only sparse. And D denotes the dimension of the latent space, or we can take it to be the maximum dimension of the two latent spaces, you know, number of people, number of movies. So given an observed data matrix, can we learn this? So I want to know the likelihood that, you know, this movie is going to be 4 out of 5 for you. And ideally, I'd like to estimate this for a sparse graph, that is P going like 1 over n, constant degree, that I don't have to have a number of movies going to infinity as, have rated a number of movies going to infinity as the number of movies in the database goes to infinity, okay? So Chatterjee did not quite have this, so it's not useful in that regime. He had a beautiful result, but it wasn't useful for P's going like 1 over n. So what is the challenge of sparsity? Well, I say that two people are similar if their neighboring movies are similar ratings on neighboring movies. But what if they have no neighboring movies? So I'm going to use an expanded neighborhood approach in which I go from movies to people to movies to people to movies to people until I find overlap. And then the birthday paradox tells me that this boundary has to be at least square root of n to get some overlap. And I'm going to look at a radius. I'm going to have to go out to a radius where P is the sampling density of order log n over log Pn, and compare the products of the ratings along the paths. And when I do that, I get the following theorem, that if W is Lipschitz and rank D and data points are observed with a probability scaling like 1 over n, then with high probability, I am going to be able to do this estimate. The mean square error is going to go to 0. This is much better than the previous result. We can do it with general bounded noise, with Graphon estimation. So that is an application. So here is the summary. We can go from a graph to a Graphon by taking a limit. Given a Graphon, we can generate random graphs consistent with that. And if we're careful, we can also, in many cases, tell you that you are able to statistically consistently estimate that. Let's see. I have a more detailed summary, but that's not important. Just remember graphs to Graphons and back to estimating graphs. Thanks for your attention.
Yeah, thank you very much for a great talk. So now there's the question and answer session. So I would ask the audience to post their questions in the question and answer tool.
So I'm going to stop sharing for now. I'll open it up again if I need to.
Sure. Yeah, are there any questions?
Oh, let me look at the chat. Okay,
yeah, so maybe I start with a question. I mean, you talked about differential privacy, so edge privacy versus connection between edges. So you said that one is a bit more meaningful than the other. Could you maybe elaborate on that a bit more?
Sure. Okay. I am a person, okay? And so I want to know what happens if I'm in the network or not in the network, and is it going to be similar? Because I'm associated with a node in the network. Edge privacy says if I pull out an edge, how similar are those going to be? That's pulling out some connections. So if I pull out my connection to you, what are the differences going to be in those answers? But I want to protect myself, not just from what's exposed by my connection to you, but from what's exposed by my connection to everyone else. So I want to know if I get the induced graph that you get by pulling out me and all my connections, are the answers I'm going to get going to be similar to what I get with me in there? And if they're not, that might make me very uncomfortable, and I might not want to be in that.
Okay, thank you. So we have another question by Zisheng Huang. He's asking, can you elaborate more about how to go from Graphon back to graphs for estimation purposes?
Okay. So from Graphons back to graphs for estimation purposes. Probably could pull up a slide from someplace else, but let me, okay. So what I land up doing, okay, is I land up basically in the guts of the proof, what I land up doing is that I land up taking the best block model approximation that I can get. Now, I don't want to do some of the standard kinds of estimation. I land up doing kind of a difference in an L2 norm. Some of the standard kinds of estimation, MLA and things, would actually not be very good because I would have things diverging in the cases that I care about. Okay, so I land up having to control that, and that really involves going into the guts of the Samaretti partitions that are representing the graph. But the big thing is that I am basically approximating it by the best possible equivalence class of block models that I can use for it. I don't know if that's helpful.
Yeah, so the next question is from Harun Prim. He's asking whether there is actually a software library which is developed, which one can apply.
I don't have a software library, but many people use Graphon estimation now, both rigorously and non-rigorously. It's very popular, and the reason it's popular is clear, because people were estimating with stochastic block models, and of course what they found was that the K of the stochastic block model, the number of species you had to have, the number of colors, went to infinity with n, and you landed up in your estimates overfitting. And so, you know, it's the standard thing that what you want to do is you want to fit non-parametrically if you've got something of really large scale. And there are people who do this. You can just look it up. I mean, I should know it, but I don't. But there are a lot of people who do Graphon estimation. You know, they're not proving the theorems. Typically, they're not the same ones who are proving the theorems about under what circumstances it is consistent, but they seem to work remarkably well in practice and much better than stochastic block models.
Okay, thank you. So the next question is from Licio Romao, and he would like to know, from all the notions of convergence that you mentioned before, how regular is the topology generated by these norms? Are they, for instance, all metrizable?
Where are we?
So this is a question which is posted in the chat, actually.
Oh, this is a question from the chat. Okay. Okay. So they are metrizable. So what we we look at is there's a lot of measure theory in this. So we have to be careful. We do have metrics, okay? We have to be very careful about the metrics that we use. We have to be very careful about the way we define them in terms of the Borel sets and everything. So we have, I mean, on the analog of the uniqueness paper for sparse graphs, you know, Christian and I did the uniqueness paper for the dense graphs, uniqueness up to measure preserving bijections. We did that with Lotzi-Lovas Sr. We did, for this new kind of graphon that lives on the positive unit square, we did that with Lotzi-Lovas Jr. We actually put it in a volume for Lotzi-Lovas Sr.'s birthday. It is over 100 pages of very painful measure theory to make sure that we could control this. So if, if you want to look at something, look at the paper with LM, Lotzi Miklos Lovas, me and Christian Borgs, which is over 100 pages, which came out a couple of years ago, in which we really deal with all of this. And there's a lot that we have to be careful about. Yes.
Okay. Thank you. So the next question is from Naoki Saito, and he is interested in hearing what to do with directed graphs, because graphons seem to deal with only undirected graphs.
I think that's a really good question. There are certainly cases in which you want to apply it. You know, this is something that I actually would like to start a student on. There are a lot of difficulties. Just try to, but it is, I mean, then you're dealing with functions which are not symmetric on the space, right? You can certainly have functions which are not symmetric on the space. And we haven't done that in applications. People have done it, and the mathematics of it has not been, pursued as much as it should, but certainly you can think of a W which is not symmetric, and as I said, people do in applications. Okay.
Okay, thanks. So next question by Florian Klim, who's asking, has there been much work on describing the properties of graphons, for instance, generalizing a local clustering coefficient to graphons?
It depends what space of graphons you're talking about, but yes, I mean, you can actually go in. I mean, one of the first things that, Christian and I did with Bela Bolobosh and Oliver Reardon was we went in and we got a lot of results on, that maybe in principle we could have proved without graphons, but we couldn't see the forest for the trees. It's like if you tried to prove something with an interacting particle system instead of a differential equation, but you're actually trying to prove something about the differential equation because you're trying to prove something about the limiting property. You could go and deal with the interacting particle system, or you could say, let me first prove this for the differential equation, and then maybe I go back and I do, as some very good mathematicians do now, understand how the individual particles approach that differential equation. But you don't have to include everything there for the effect you're looking for. And so, yes, people have defined all kinds of objects on the graphons, and that was kind of the whole point about them. They are in many ways, and almost always, easier to use for the global properties, like like you might talk about an average clustering across the graph.
Thank you. So next is
let me just see though, you cannot, okay. But he's talking about unequal. Okay. So no, we are building these independently. If I wanted to build them not independently, what I might try to do is start from the newer Graphon model, which is kind of built on the Carone-Fox model, and try to change the process, okay? Try to look at the change of it over time. So one of the things that you get out of this second Graphon model is that you get real differences in the early and the late nodes, okay? Because you've got this Poisson process, which is generating them, and they only pop into the graph once somebody is connected with them, and things like that. And so what we get out of limits from that are we have cores, and then we have some pairs, and then we have some isolated ones. So you might try to do something there.
Okay, and the last question by Jalil Kasemitaba. He's interested in compares the Graphon estimation with other more classical approaches.
So I'm not sure which more classical approaches you're talking about. I think, you know, if you want to do a stochastic block model or some of the other ones that people have done before, the problem is they were not stable to misspecification. Okay, so if I really am an underlying stochastic block model, then I'm going to get something great out of using a stochastic block model approximation. What we really wanted to do and what we came up with was something that, you know, was stable to misspecification. You weren't assuming something of a particular form in advance. So I guess that would be my answer. Why did people try to start moving towards these non-parametric things? Just for stability to misspecification.
Okay, thank you very much. So now I hand over again to Mason.
You're muted, Mason.
Could you unmute?
Got it. Yeah, usually people prefer that way. I'm gonna just announce the next talk in this series. It's going to be given by Andrea Bertozzi from UCLA. This will take place on June 22nd at 1 o'clock Eastern. The title of the talk next week will be Graphical Models in Machine Learning, Networks, and Uncertainty Quantification. And thank you everybody for coming.
Thank you.